There's Mr. Handsome Jack Zampolin.
Hit,
Yo,
yo,
what's up,
what up,
Jay?
Saga?
How's it going, dude? Long time no talk. How's dad life?
Daddy, I do a lot of dad stuff, and yeah, it's kind of standard.
That's awesome, dude. I got a little girl that's about 5 months away, so I'll be joining Cosmos Dad Club with you.
Oh, that's right. That's very exciting. There's a lot of Cosmos kids these days.
Bull market vibes, bro.
Yeah, yeah,
Or
it's good. Well, so you got to start those plans in the bull market, I guess.
exactly, man. Uh, yeah, so I think we can probably get it started here. Um, I'm not sure if you had a chance to look over the paper that we just published, Jack, but it's a really good summary on just ETH 2.0 versus Tendermint, the pros and cons of each. I figured we could get it started off with just a high overview question of like, how do you view like what is consensus mechanism in the blockchain world? And then follow question will be how do you view proof of work versus proof of stake as a consensus mechanism?
So I mean, consensus is kind of key to this entire space. And my introduction to consensus from a technical perspective was actually with Raft and Paxos. And then through that, proof of work was around then when I was sort of learning that. But Raft and Paxos kind of make a lot more sense as basic consensus algorithms, and they're sort of precursors to the modern proof of stake stuff. As far as proof of work versus proof of stake, for a long time it's kind of seemed obvious that there's only going to be one proof of work chain, and that any other proof of work chains are sort of inherently unsafe, and that we will need proof of stake um, to scale blockchains kind of more generally. Proof of work is an extremely expensive way of securing chains, but it has some unique security properties that make it good for reasons. And yeah, so anyway, that's kind of a top level idea. Where can we dig in there, Drew?
Yeah, I think you did a really great job. I also am of the point of view that there can only be one proof of work chain, and Bitcoin seems to be filling that role. It's pretty exciting to see Ethereum fork off and do their own proof of stake mechanism. So I guess to dive in a little further, maybe we can just go into Tendermint, which was, I'd say, arguably the first real in production decentralized launch proof of stake consensus mechanism. I mean, you could argue EOS or something was first, but there was a
Well, yeah,
fully centralized launch. Whatever. Let's just say
yeah.
Tendermint's the
Well,
first.
those also weren't fault tolerant. Oh, I see we've got a Jin here too. Those also weren't Byzantine fault tolerant, and the algorithms that they're using to come to consensus have some formal issues with them. So yes,
Hello.
hey Jen, what's going on, man?
What up, man? Long
Um,
time no talk.
yeah, I know. Good to see you. Are you still in California?
Nope.
Nope. Awesome. Um, yeah, we'll catch up on that stuff later. Um, but when we're yeah, Tendermint was kind of the first proof of stake algorithm. Um, the work that Jay did and Bucky and the sort of early Cosmos crew was critical to a lot of the early decisions and discussions around proof of stake in the Ethereum community as well. Um, so, we here in Cosmos have long been kind of proof of stake pioneers, and we've been the first people to productionize that work and sort of like bring it to the masses. I think distributed consensus is one of the most interesting applications of computing that's ever been developed, because what it really does is allow people to maintain databases collectively and to share ownership of those databases in a way that's irrevocable once it's created. And that is kind of fundamentally different from all other previous database technologies in which there was one person or entity with a key. And no matter how much legal engineering you do, there is just always this practical issue that somebody can come in and change the records. Um, And with blockchain, that kind of solves that issue. And proof of stake is the way we kind of scale this to the masses.
Yeah, the whole idea of a shared database or shared infrastructure between a large group of people is very interesting. And then you have to look at the difference of where proof of work and proof of stake, it's even a different level of ownership over that network, in my opinion. I mean, you can see this with the whole history of Cosmos with the various governance proposals where you can do some more exotic things, you could say, or change some different variables, but do it as a team and not in like a backroom decision that a group of developers do and just push to the community, which I think is very interesting.
Yeah, I mean, like in a Postgres database or in a SQL database, like they run at, Facebook and Twitter, and, those are all just like big centralized databases. At the end of the day, it's like one person who has the key, and like, anyone with access to the systems can go in there and mess with them. And that's just a very different trust model than this entire community of hundreds of validators has the key.
Yeah, for sure. It's a whole new ballgame. I loved your point around this, around distributed consensus being one of the most interesting areas of computer science in history, really. It's such a whole new way of looking at computer systems and groups of people and economic organizations. So I feel like I'm kind of getting a little bit off track, so I'll come back. Let's dive into ETH 2.0 a little bit and look at how it is different from Tendermint. And I'd recommend everyone in here, if you're interested and you haven't done your deep dive yet, feel free to read the research article we just posted. It does a really good job of looking at the pros and cons of ETH2 versus Tendermint. So yeah, take it away, Jack. What do you think about ETH2? What are some strong parts of Casper and all that good stuff?
Yeah, I think that there's this trilemma in distributed consensus, and there's liveness, safety, and partition tolerance. And basically what it comes down to is you can choose two. So partition tolerance is if, part of the network goes down, how does the network deal with that? And pretty much all distributed consensus protocols choose partition tolerance. So really your choice is between safety and liveness.
And is another word for that just like not forking?
Yes, exactly.
Okay, cool.
Pretty much the design space is a choice between safety and liveness. So in Tendermint, we have long chosen safety, and the Tendermint protocol will stop if safety is threatened, and allow the human operators that sort of underlie the network to drop back into what we here call social consensus in order to go fix the network. Now, the Ethereum community has actually chosen liveness over safety, which is a different set of trade-offs, and they have probabilistic finality, the block when they've got signatures from the full 2/3 of the validator set, but that may take some time. So they sort of move the chain forward without the full set of signatures based on probabilities. This can lead to the ability to fork potentially. So yeah, they've made an entirely different set of trade-offs, and fundamentally it's in order to enable a large number of individual machines to validate. Now, we chose a much smaller number of machines to validate. So like the average Cosmos chain has around 150 validators. It would be pretty easy to move this up to around 300 to 400 with current block times. But we haven't really tried to optimize for a large number of validators. Our working theory is that there's only a smaller number of entities in the world that can run secure validators. So the ability for a chain to have many validators is not necessarily beneficial and doesn't really add a whole ton of security. Another thing that they've done is capped the amount of stake that can be staked to each individual validator. This basically ensures that if you have, say, thousands of Ethereum, i.e. big whales, and you want to stake it, you have to spin up a very large engineering effort to manage hundreds of different virtual machines. And this dynamic encourages scale. So it really plays into the hands of organizations that have really competent DevOps and can spin up large server clusters. And we're talking thousands to tens of thousands of machines sometimes. There are, I think, 400,000 Ethereum 2 validators. And of that, around a third is controlled by two entities. So if there's 400,000 and a third is controlled by two entities, each of those entities has on the order of tens of thousands of individual virtual machines validating on Eth2. That's a huge maintenance burden. And, I think, frankly, it has ended up causing a lot more centralization of validation power within Eth2, because instead of trying to democratize it and make it easy for anyone to run a validator that can accept any amount of stake, they've capped the amount of stake in each validator and basically forced anyone who wants to run at scale to run these huge server clusters. And I think that that's why they've ended up with a smaller number of entities able to censor transactions on Eth2.
And it's really interesting how that evolves with the fact that staking derivatives are somewhat inevitable. So they could have predicted Lido, but that didn't change how they engineered it. So now we have Lido having such a massive portion of the stake, and a lot of it just due to convenience and liquidity, where liquidity is king. And if the most liquid stake derivative is Lido, then everyone's going to flock there. So that's kind of an interesting consequence. But Jack did a really good job of going through a lot of the main pieces in the paper that we wrote. I'd say the three main sections just talk about the finality of your blockchain, and then the distribution of stake on your blockchain, and then lastly, validation requirements for your blockchain. So Jack really did cover all three of those pretty well. But I'm just going to dig in a little bit deeper into the finality on the blockchain part, because I think that's really important for the future that we are envisioning with composability, and that's what Ethereum prided itself on. So when we started this paper, I was very curious myself, like when does a transaction become final? Like Jack was saying, at first it's probabilistic, and then after a period of time, it gets set in stone as an unchangeable. And after doing some math, it looks like the fastest, assuming there is no attacks on the system, roughly the fastest you can expect a transaction to go final is about 12 minutes. And the slowest you can expect is somewhere in the neighborhood of 20 minutes. So I think that's a very interesting design trade-off when you start thinking about the Ethereum roadmap with L2s and rollups and danksharding and all this stuff, that you're going to need the IBC level composability between these subsystems, but that will have a 15-ish minute delay on it, which kills a lot of the composability. So feel free to go off any of that, Jack. Kind of just
for
a second.
I mean, the sort of instant finality thing in Tendermint is a huge benefit for interacting with other ecosystems, and this gets down to how IBC is developed, and it really relies on light clients. And I think light clients are a really interesting piece of blockchains, because if we want blockchains to actually be decentralized, any client, i.e. a mobile phone or somebody with a very low-powered computer, should be able to verify that they are talking to the correct blockchain and do that in a performant way, without having to download gigabytes and gigabytes of data. And this is what light clients do. They allow clients like mobile phones or other sort of resource-constrained areas to download only kilobytes of data, something that's really reasonable over even shaky internet connections, and verify that the chain that they're talking to is accurate. And they would only have to do this once every week or two, potentially. So with this in mind, light clients are this very key component of decentralized systems that allow the different actors using them to verify the correctness of the different endpoints that they're talking to, and they add a lot of trust into the system. And here in Cosmos and Tendermint, we built with light clients as a first-class citizen. So it's been a major feature of the protocol that's been live since around 2019. And we put a lot of work into that. And why is that? That's because with IBC, the security from IBC comes from these light clients. This is another thing that Ethereum sacrificed with the trade-offs that they made with their consensus, was the ability to easily build light clients for the ETH2 chain. It is really, because of the large number of validators, it's extremely hard and requires advanced cryptography to succinctly verify the state of the ETH2 chain from something like a mobile phone. And that's, I think that that's really problematic. Other ecosystems, things like Solana, it's impossible to build a light client for their protocol. And that kind of has its own trade-offs. But yeah, does that sort of answer what you were asking there, Joe?
Yeah, I think you did a really great job. And then I'm trying to be as unbiased as possible through this and provide the bull case for ETH, even though Jack and I are both huge cosmonauts. So the bull case for why they chose Casper
How about
and their
this? I'll try not to fade ETH too hard.
No, it's fine. I'll always be here as the trying to be the moderator. You can go as hard as you want in the paint. Okay, so the reason why they, let's just all say it here. Ethereum developers are very smart people. They're incredibly intelligent, and they thought about all the consequences of their design when they made their decisions. So the trade-off of this long finality that they have, let's just say 15-minute finality, is that the network can be attacked. Like, let's say 40% of the network goes rogue and starts attacking the network. In Tendermint, the chain would just shut down. And then human consensus would be required to figure out who is the misbehaving actor, what is like the correct true chain, and then how do we do the slashing and whatever to get the chain back going. In Ethereum's case, the network would not go down, it would just start forking. And there would be different sources of truth. It'd be harder to find the source of truth, but the network would slowly start slashing the entity that was the shorter stake. So the less powerful stake would slowly start getting slashed without bringing down the network. So that makes sense if you're Ethereum and you're trying to build the global settlement layer that never goes down no matter what happens. It actually does make sense to do that. I just think once you factor in the roll up future, L2s, dank sharding, all that, I think it might break down a little bit because you want the interoperability between these L2s and these roll ups, or else you're going to lose the composability that Ethereum is famous for. So anyway,
dank sharding.
Have you not heard that yet?
I mean, I've definitely heard of dank sharding.
Okay, yeah.
It's like this whole idea around sharding is not necessarily something I think is really feasible. B, if you're in this environment, you're going to break composability. There's literally no ability to not do that. So, what we've been building here in Cosmos is, and what most of what we're doing at Strangelove is working to re-enable asynchronous composability. Working to re-enable asynchronous composability within the IBC ecosystem. So what does that mean? In computer programming, there's this ability to lock a specific portion of memory or storage and say, I need to do some stuff with this memory and I want everything else to stop. And that's basically how it works with every transaction. In Ethereum, every transaction, there's this lock on global state, and that transaction can do all the stuff it needs. That's really slow. And if you need to speed up and support many, many more users on top of that system, you kind of need to change the way that works. And that's the cost of the type of composability that Ethereum has. And I think they've done a lot of work to try to keep that composability when it's going to be fundamentally impossible in a lot of ways. Now, this is basically do this and then do this next thing, and there can't be any latency or time in between those two things. And there's no concept of that. What asynchronous composability adds in is say, do this, and then wait for that to be finished, and then do this other thing. And that's actually a very well-known programming paradigm. This exists in many programming languages. It just requires custom tooling to help deal with the latency and to help deal with the many different error cases that crop up in a system like that. HTTP and the internet that we use is fundamentally asynchronous composability. We call them APIs. And there's been this massive boom in APIs as services and products over the last 20 years. So asynchronous composability works at scale. And that's what we're building in IBC. And, that is much more scalable than synchronous composability, which is cool and interesting from a, I think more of a...
It's extremely efficient. I mean, synchronous composability would be like the early days of Ethereum L1,
it's
where
extremely effective. It's not efficient though, because
effective. Okay, yeah.
Yeah, it only enables one actor to have that synchronous composability given time. And like a lot of the MEV work that we're seeing in Ethereum is due to the lack of asynchronous composability.
Okay, yeah, I got you. I was just thinking more like a single database, like everything on that database is so closely connected to each other that it's very interoperable with each other, but that means that everything's on a single database, which is not what the ETH future roadmap is due to it's kind of conflicting, right? That you have the roadmap where they have 15-minute finality, but everything is built off L2s and rollups. So like
well,
it's
you can kind of think of similarly to like multi-threaded computation.
Exactly.
Right? It's like if every application is siloed, then it's okay, but then you don't need composability. But if every application is not siloed and is talking to tons and tons of other applications, then it doesn't work anyway. So it's like then it's like, why are we designing for this, right? I think that's and usually that's the same thing as multi-threaded computation, right? When like a thread, for example, tries to talk to another thread, if they're not talking to other threads, it's really fast. But if they are talking to other threads, then it's slow because it's thrashing, right? So it's like you gotta figure out a way to design this in a correct fashion. But
I remember, just as I was doing embedded iOS for a long time, and the ultimate form that this took at least in iOS, was the programmer was given the opportunity to use these structures called blocks, and they're basically like, yeah, we're not going to let you do the scheduling anymore and like deal with the kernel and the channels and all this. Just submit your workload, and the operating system will find it, and it's going to route it in the most effective way. So I wonder if something similar to that is going to arrive.
I mean, I think that's like what we're building with interchain accounts and interchain queries. And we just need to build better testing and abstractions on top of that within the programming languages that we use to help developers manage this complexity in a sane way. I like to think about this as the project to create promises over IBC. Like, it would be great if in your contract you can say, I want to send this IBC command out and I'm going to get a promise back. And whenever that resolves, we're going to do some stuff. Like, that's very buildable with what we have now. It just requires quite a bit of work, and that's what we're working on.
So this is a really fascinating topic, because I think what's happened with both security and computation is, like, my whole background is in silicon. So it used to be you relied on the individual device for its own security and its own scheduling. You allow the Linux kernel, you say, hey, this program needs to run eventually, and the kernel will figure it out. You provide some priority. With proof of stake, you're now a network node security and a network node scheduling. So both the security and the scheduling have been moved away from the individual device. And then when it comes to, like, when should this workload be marshaled, I think people are going to need to be able to attach dollars to it and say, I want to bump my thing up the priority list by attaching more money to it and encouraging more people to want to process my workload. So you're basically building decentralized AWS with bonus fees at that point.
Yeah, I mean, this is sort of like the broader question of how much do applications value sovereignty and how much do they care about platform risk? And the people building these huge systems that are essentially end up being this like huge serverless system where you've just got contracts running in this like cloud of underlying compute, and there's this kind of questionable trust model underneath it. they think that everything is going to run on these like hyperscale blockchains. And that is like potentially a huge direction to go. There's a ton of money behind those directions. I think it's really the right move for a lot of applications, but there's a whole class of applications thinking things like governance, DEXs, different social media things, potentially different gaming things, potentially that will require their own ones. But Saga is also sort of entering into this market and competing in this world of how to offer this sort of like decentralized serverless platform for developers, and how do we build that out?
That is correct. At the very end of this, we will get to where Saga fits in. Rebecca just joined, our CEO, so that's great. Hello,
hey guys.
Rebecca.
Hey, Jack. Thanks so much for being on.
Hey, Rebecca.
Hey. So I don't want to disrupt the discussion. And apologies for being late. I had to jump off another call, but really, really thrilled to have you here, Jack.
Yeah, thank you.
That sounds good. I'll get on the topic of today, the Eth2 versus Tendermint. Oh, yeah. Go ahead, Jen.
Question, actually?
Yeah, go ahead, Jen.
Yeah, please.
I've been thinking a little bit about this. What's stopping a Cosmos chain to implement something similar to the way that Eth2 does it, which is like whenever a Cosmos chain is about to halt, can't they just restart and also slash the people who are in the minority and just keep doing that? And eventually the chain will also just start producing blocks again,
So this is like right now, the way that this works is Tendermint assumes that the human operators will make that change and restart the chain. We could add automation around that, but that adds additional sort of trust assumptions on the validator set.
And risks, right? Like when Juno had its like non-deterministic fork, like what do you do then?
There's 100. If there's 100 different,
essentially
exactly.
There won't be like a settlement, right? Because it will just constantly go down. So they can just go back to the snapshot before it started happening, anyways. So this is not a if there is an actual attack, it can still like produce blocks in the future if you just use some form of validator orchestration to just restart it and keep slashing, right?
Yeah. I mean, like, I think that the validators that are connected to the peer-to-peer network would be oversecting peer-to-peer networks. They would get hashes from the two sides of the fork. Based on the number of votes on each side of the fork, what they would do is make a sort of irregular state modification that slashes the validators that are on the wrong side of the fork and moves forward. But what is the wrong side of the fork? Because if the chain is halted, then it's greater than 1/3 of stake that is able to halt the chain. But that doesn't necessarily mean that the other side of the fork has greater than 2/3 of stake that's required to alter state. So if you allow less than 2/3 of validators to alter state, that changes the fundamental security assumptions with proof of stake and turns it into a majority. This is why we have to drop back to the human consensus. And like, maybe there's 60% of validators that are like, yo, this guy over here bought up all the stake and he's trying to fuck us over, and we're going to slash his stake and force his validator out of the chain and then restart. That requires the human consensus. And I think this is one of the beautiful things about IBC. Like, we could easily imagine a system where a bare majority is able to rewrite state, and then that kind of fixes this issue in a way. And the only case in which we would halt is if between 51 and 33% of stake is offline. And there's a chain on IBC that might make that trade-off. And the other chains within IBC can sort of interoperate with it seamlessly, and that chain can rise or fail on its own merits. And I think a great example of somebody sort of messing with the fundamental security model is looking at what happened to Terra. They had this the ability to sort of print an unlimited amount of their staking token, which represented this sort of existential risk to the proof of stake security model. That vulnerability, one might say, ended up getting exploited, and then the IBC network kind of cut them off. And this is, I anticipate the way that this is going to happen in the future, but the beauty of IBC is that it does allow many of these different kinds of experiments with these different consensus mechanisms to flourish.
Cool. All right, well, I'll jump back into the paper, and the next section is around the distribution of stake. Jack kind of went into this earlier, but I'll do a little just gloss over it and then let Jack take back over. So there's something called the Nakamoto coefficient, which is roughly like how many validators or how many entities does it take to control 33% of your chain, because that's roughly the number where you can start causing havoc, cause like finality issues or halts or whatever. So if you look at something like the Cosmos Hub, you see that only 7 validators control 33% of the stake. So that may be alarming to some. That may sound like centralization. But then you look at Ethereum proof of stake, and each validator only has 30 ETH. So that means that each validator is on a level playing field, in theory. And currently, there's over 420,000 validators. That all sounds really great in theory, and it's like a great meme. But if you dig a little deeper, as Jack noted, entities like Coinbase are running 50 to 100,000 validators just themselves. So then you get into the fact that, okay, there's inherently Sybil, what we call Sybil, in the Ethereum proof of stake chain, and it's very hard to tell how large an entity is. Where in Cosmos, you get the benefit, you know exactly how large Coinbase's validator is. There's no ambiguity about it.
Exactly.
So yeah, Jack, feel free to go ahead on whatever you want from that.
I mean, I do fundamentally agree with what you're saying here, and this has been like Jay and Ethan and Zachy and a lot of the early Cosmos folks were talking to Vitalik and the early Ethereum proof of stake folks. And if you remember, the Ethereum proof of stake conversation started back in 2015, 2016, and they went on kind of a very winding path. And a lot of their initial directions ended up being kind of dry wells. And they came back to a lot of the work that we've been doing in Tendermint in a way. And if you look at, interchain security, which you guys are implementing, looks a lot like this. Some of the sharding, the early sharding implementations they decided on, and like that's great. That's a really valid direction for trying to do this. And the downside from their perspective is that it requires this sort of asynchronous composability that we can fix with better programming models that are well worn and have been used in many other sort of disciplines of computing. And the other direction is this sort of settlement layer and the ability to have all these roll-ups, and they've got this sort of like to figure out how to do composability between the roll-ups. There's stuff there, but again, it runs into a lot of these asynchronous composability issues, and that looks a lot like what Celestia is building and will likely ship before ETH has the full system ready. So, my view on Ethereum, like it is a lot of talented folks, but I've always thought they've been kind of off base on some fundamental values, and this is one of the areas where I think Cosmos is stronger. We're a lot more pragmatic, and we look at this stuff a lot more from how does this actually work in the real world? We do a lot better job of bringing in history from outside of the blockchain space, and I think that what we're building is going to stand the test of time because of that.
Yeah, I fully agree. And just to dive in a little bit deeper into that one point. So when I talked about dank sharding earlier, that's actually Ethereum building an equivalent to Celestia. It's more or less using data availability sampling to leverage all the number of nodes.
So dank sharding just means Celestia. I'm gonna mentally translate that in the future.
Yes, do that. So it is they are not doing the full stack. They are just sharding the data availability layer and then using data availability sampling to get the exponential improvements from that. But it's not the first. All right, I'm going into some weeds here. But the first version they're planning on shipping is called proto dank sharding, which has like not the full like economic. My understanding is it doesn't have the full and economic intertwining in there to make it like a full Celestia equivalent. But their final vision, dank sharding, is Celestia. So anyway, that's fun little
real dank.
So again,
I mean, that architecture is incredibly cool, and you know, really looking forward to building out IBC into that world. The client abstraction that we built in IBC is sufficiently abstract to do like clients. It can do proof of authority type authentication methods, and it can also fit in ZK snarks and starks and the various different types of cryptography that are required to validate all of these rollups. And, you know, IBC itself doesn't really care if the other side of the connection is a database or this huge public blockchain or a rollup. It will move your packets. And with that transport layer as a primitive, then then building this sort of asynchronous composability on top of it is much more possible. And, you know, Saga is going to be a huge part of that world as this sort of hub of different applications that are being developed. Really excited to see all of this sort of together over the next couple of years.
Oh, yeah, I totally agree, Jack. And just to continue my thread of also tried to be unbiased as possible, I'm going to give the bull case for why ETH2 chose their distribution of stake method. And I think it can be boiled down, or like the biggest reason is something called like how many throats to choke. Like how many individual people can you transparently see if you go to them and then, I don't know if this is government or whatever, tells them, hey, corrupt the chain, lie, cheat, steal, whatever, how many people do you have to go to? And in theory, the Cosmos Hub, that number is 7. Which sounds pretty dangerous. And I mean, if you drink the Kool-Aid and you look at Ethereum, you'd have to say, wow, you'd have to go to 120,000 validators to do that. That sounds incredibly difficult. How are you ever going to do that? We talked about it earlier around how that's not really true because of Coinbase, Lido, Kraken, Binance, etc. But that's the bull case for why they chose that.
Yeah, I think the way to say it is it might not be fully decentralized. The validator set might not be fully decentralized today, but there's a possibility of it becoming like that way in the future, right? Where, you know, like literally every mobile phone, everybody's laptop is running like a tiny little consensus node, and it's possible.
I don't think so, because if the ETH theory plays out, then it's going to cost 32 ETH. So then you're going to have, and let's just say that it really does play out and ETH goes to 10,000 or whatever they're expecting, you're looking at $320,000. Like, I don't think anyone in their mind is going to have $320,000 on their phone with them walking around that can also be slashed from downtime. Like, that doesn't sound like a realistic future to me. But sure, if you want to like say that possibly that's why they chose that decision. I mean, well, this kind of leads right into the next one, actually. I'll just jump right into it. Validation requirements. One of the benefits of Eth2.0 is that you can run a validator on fairly humble hardware, I'd call it. $1,000 laptop, you can run a Ethereum 2.0 node right now, versus Cosmos, and especially some of the more high activity chains, high throughput chains. You're never going to get that. You're going to have to buy some actual real good computing hardware or do some sort of cloud compute non-bare metal thing. So I can dive more into it later, but I'll let Jack step in here with any thoughts.
Yeah, you know, this is like back to the Bitcoin fundamentalism of you need to be able to run it on a Raspberry Pi. So as a side note, you can run a Tendermint validator on a Raspberry Pi. And Jacob from Notional has been doing a bunch of work on that. The memory and CPU requirements are not insane. As long as the CPU is decently fast, It doesn't need to have a ton of threads. It's the single thread performance of the individual CPU that kind of makes the difference. And then beyond that, it's kind of disk and networking, which do not depend on the underlying computer itself. So the requirements to run a Cosmos node aren't as high as people think they are. B, we have not really optimized storage at all. And there's actually a lot of like wasted space in the storage side of things. There's a lot of database optimization work that we've kind of left undone. And I think that it will be very easy to go back and kind of do that database optimization work. And a lot of it is ongoing right now. So yeah, I don't know. Does anyone else have thoughts on this?
I think with Eth2 also coming back to the fact that you have to run multiple validator nodes, the complexity of running like a single node might be less, but the complexity of running like 100,000 nodes is quite high, and making sure that every single one of them is performing at the threshold that it needs to be adds a lot of complexity, which means that as an aggregate, you like the operations of it becomes harder as the bigger you become. And so I think there's some complexity that comes from that aspect that Tendermint doesn't have, in my opinion. But
I kind of want to comment because like both Jin and I worked at Intel, and then like I worked before joining Saga. I was in Silicon for the last 10, 12 years. And one of the things that really attracted me to the Cosmos ecosystem is, one, it seems to be gaining a lot of people and founders who I think are very technology driven, who are about the technology. So I think that's fascinating. The other thing is it kind of reminds me of a parallel situation that happened in IoT 10 years ago during the maker movement, where people would get a single board computer and it was very hard to connect it to the internet. And then a lot of work went into optimizing what was called, the developer experience, user experience, so that you could get your IoT device, set it up, connect it, make it live in like 10 minutes. That took a long time. That was quite hard. And what you just said about the Raspberry Pi and the Lite client, I think there's the potential for some, validator experience. And a set of tools were created to solve this problem on the IoT side, like Baylina and Mender, and they address the problem. So I think that I could see a world where these validators are this experience of setting up these streamlined validators gets easier and easier through some of these automation tools that were already created in the prior era.
Yeah, as far as the validator automation tools, this has been a passion of mine. Like I got into blockchain after working in the traditional cloud world. And we built out amazing automation tooling for the database we worked on. And that was how we ended up getting user adoption. And I brought a lot of those lessons that I had learned doing that work into Cosmos. And I think that this is kind of one of the fundamental differentiators we have. And one of the big areas I've been working with the Saga team on is helping to ensure that this huge explosion in huge explosion in complexity that's going to come from requiring validators to run many chains is manageable, understandable, and scalable for those validators. And it's tools like Horcrux that enable you to take the key signing part of the architecture of a validator and shard it into something that's highly available that can then serve signatures for many, many different chains. These are the types of like core technology work that then get wrapped with things like Helm charts and different deployment procedures and standard deployments that come together to make an operator experience nice and easy. And monitoring at every layer of the stack, like as you can see, there's a large number of tasks here that are required of operators. And the more that we as engineers can help ease that burden, we're going to have more and more operators, and we're going to make it easier and easier for operators. So I think that that's one of the things that I'm most excited about Saga about is that that's what you guys are really thinking about at the core.
Right. I mean, orchestrating a bunch of ETH nodes is conceptually at least pretty similar to orchestrating a bunch of Saga chainlets, right? So you're just in the first scenario, you're validating the same chain, where in the second scenario, you're validating technically different chains, but like the actual work that goes into it is probably pretty similar, where you need to spin it up, make sure monitoring is there, and it's going to be a different binary that runs, and you're going to have to make sure that they're performing properly. So I think that's really interesting. Do you know, Jack, actually in Eth2.0, like with Coinbase running like all these, like what kinds of like orchestration and coordination software exists right now, or is it all just kind of in-house and not shared across the different validators? Do you know?
You there, Jack? Did you get that?
Sorry, I was talking. Thank you, Jen. This is where I think ETH2 made the biggest mistake, and what is the largest centralization vector for ETH2. All of the various operators have kept those techniques secret because they take a lot of money to develop, and there's a huge competitive advantage in having the best ability to manage and do these from a low cost perspective, because if you can do that, then you can beat all your competitors and get all the delegations. But what we end up with is a tragedy of the commons where there's only one entity controlling the chain. So how are they doing that? I can guess at it because I know how to scale these type of things, and like we're working on a Kubernetes operator for Cosmos nodes that enables you to, really forget about a lot of the blocking and tackling, things like scheduling upgrades, things like basic monitoring, things like node failover, things like snapshots that are required to kind of operationalize running huge arrays of different Cosmos nodes. That work, we're going to contribute to the open source, but in the Ethereum community has all been kept closed. So how are they doing it? There's only a handful of ways to run tens of thousands of computers, and most of them have kind of converged around Kubernetes and friends at this point, or building deeply into an individual cloud provider's APIs. So like working closely with the Amazon APIs in a tool like Terraform to be able to easily spin up and manage your infrastructure. Or the other option is having these like large Kubernetes clusters where you're managing the deployment of objects on top of those using something like Compose, or any of the bevy of different Kubernetes tooling that exists out there.
So I think these guys did a very good job of showing the downsides to having 400,000 validators and low requirements. But let me give the bull case real quick. So they have really low validator requirements for the hardware. And the benefit is, and all the previous decisions we described above, there's a crap load of validators. Like it's going to be upwards of 500 to 600,000 plus at some point, maybe a million or something like that. And the benefits you can get from that come when they do their dank sharding. Because with data availability sampling, you actually get an improvement for every additional node on the network, because each one is just doing a small percentage of the data availability sampling and leading to exponential increases on how much data the whole network can hold. So at a future end state, there's a possibility that the Ethereum 2 network, if proto dank sharding ships well and everything goes well, there could be an incredible amount of data availability provided by the ETH2 layer. So that's my bull case. That's the best I can do.
I just have an issue with the naming. Proto dank sharding is terrible. Sorry, Rex.
Agreed. I first heard it when I was at Ethereum Denver, and I was like, what? Because it came out of left field, and like overnight it became like the dominant roadmap for ETH. And I'm like, how did this go from me never hearing it to the dominant roadmap like overnight? It was like shocking.
Because the Celestia guys are fucking smart.
I think that's a pretty fair take, Jack.
They know their target market.
Yeah, and I mean the improvements of data availability sampling is amazing. It's like the first time that you do like a linear amount more of work and get an exponential amount more of safe data availability, which is incredible. But my opinion is that how are they gonna outship Celestia when they're just building just that? Like I don't understand how that's even possible, given how smart Celestia is and how tough of a challenge it seems to be. Because they're just trying to design that one piece, and it's tough.
I mean, just just to again toot our horn for what we do here in Cosmos.
I love it. I love it. Going hard in the paint.
The reason why we have the community that we do, the reason that we've been able to build the user base we have, is because we've sort of like kept this roadmap for a very long time, and we've continued to ship rapidly. When many of the other ecosystems have had these sort of like very changing roadmaps, they've had huge issues shipping. It's taken years. We have continued to get software out in front of users over and over again throughout many different forms of turmoil in this ecosystem for years. And like that is, I think, fundamental to the culture of Cosmos.
Yeah, I feel like this is an appropriate time to give a shout out to the foresight of Jay and Ethan for seeing the multi-chain vision and building Tendermint so early and knowing that IBC and the application-specific future was going to take over, and the one chain to rule them all was just not the correct narrative, even though it seemed like it was so right at the time. I think they are slowly being proven more and more right, and the market is slowly putting their chips more in that direction. So bullish Cosmos for all sorts of the different projects that are sprouting up. Nice. I feel like we did a good job covering all of the ETH2 versus Tendermint stuff. Is there any final comments that anybody on the stage would like to add for that, or should we dive into where Saga fits into this whole landscape? That sounds like a no. Okay, so where Saga fits in is we are leveraging Tendermint as our consensus mechanism, and with that we will get the fast finality and the interoperability and the composability, like Jack was saying, the asynchronous composability that we've all come to love and expect out of our DeFi crypto projects. We don't want siloed applications or siloed blockchains. Everything needs to be connected for us all to win. But at the same time, Saga, the first virtual machine that we'll be offering, is the EVM. And the reason why we chose that, well, first of all, before Evmos, there was a gap in the market for Cosmos. And second of all, there's just a massive amount of mind share and developed code base that is secure and just bright minds that have worked on and around the EVM. So we thought that is a logical first choice. But we're also not any virtual machine maxi. We are very open to, we don't know if Move is going to be the best VM, or if it's CosmWasm, which is going to be the next one in the stack, or if EVM is going to dominate for the foreseeable future. I doubt it. But yeah, I think that's where Saga fits into this. Feel free to take it away, Jack, Rebecca, Jin.
Oh, thanks so much for that, Joe. This has been a fascinating discussion. And Jack, thank you again for being on today. I do want to be mindful of the time and leave enough space on this call to ask questions as well. There are quite a number of you who have joined us today, so really appreciate it. But yeah, Joe, just a foot stomp on what you said. So we're obviously all big believers in Cosmos. We all come from the core of Cosmos, and we formed Saga in that way. We chose EVM because we see how popular it is with developers. It's true that our vision is to be VM agnostic. And so the next kind of VM that we'll support is WASM, because it's incredibly helpful for people looking to develop in Cosmos. I'm sure there will be a Solana VM coming in the future. There will be a Move VM, etc. What's exciting about those VMs as we build out the roadmap is some of them might be developed by the Saga core team. But because we see this pattern of migration, if you will, or what I like to call the Great Awakening, we see more and more projects coming off of these monolithic chains and getting onto Cosmos. There's a reason why these VMs get created. It is because a game that's on Solana, for instance, is really freaking tired of dealing with all the cruft that you have to deal with on Solana. The chain is down, you have no control over your architecture. The game mechanics it's all getting to be a little too much for these projects that are looking to scale and being serious applications with an appreciable amount of user traffic. And so they're looking for a new home, but how do they best onboard onto that new home? And so that will account for the proliferation of VMs on Saga. But yeah, just to kind of wrap it all up in a bow, what we think about first and foremost is what is going to help the developer either do better in Web3 or get onto Web3. It's very simple at the end of the day. well, it's a very simple mission statement, but in terms of actually executing on it, it's not easy. But that is ultimately what we want to do. And so when we look at what 2.0 represents versus what Tendermint is able to offer, we respect the community that Ethereum has put together. But obviously, in terms of the technology that's going to take this space forward and really open up a set of opportunities for developers, obviously, our money is on Cosmos. So with that, I definitely want to hand it over to Jack for any other remarks that he'd like to make, and then if we can open it up for questions, that'd be great.
Well, let's bring up the firing line here.
Yeah, right. Anybody in the audience that wants to ask a question, you can feel free to ping the Saga account, Jack or Rebecca. They're all hosts, and get to that. But yeah, any closing comments, Jack?
None. So.
Okay, yeah, I think we did a pretty good job of covering a lot of the top level stuff. I do recommend reading this research paper. You'll get a better idea of like actually how the mechanics work around the Ethereum epochs and how it reaches semi-finality and then true finality. We didn't actually get into that here, but I think that's best left for the paper and the visuals.
Proto finality.
Dank finality.
Yeah, there you go. I think you're just saying, so dank sharding Celestia, yeah, you can just leave it there. But anyway, this is a great conversation. I guess if there's no questions, we could probably just close it down a little bit early. We really appreciate your time, Jack, and I'm sure you got a million things going on as always. But
absolutely, we're working on this WASM light client code that would enable you to write Cosmos SDK light clients for IBC in Rust and deploy them via WASM. So yeah, all kinds of fun stuff. Just the usual.
I'm not surprised you're doing something that I hardly understand, but I'll probably be using in about a year or two. So
yeah, you'll help me shill it when it's ready.
Yeah, exactly.
All right.
Well, hey, have a good one. Thanks everybody for joining. This is great.
Thank you guys. Have a great one.
Yep. Bye bye.
Thanks everyone. Thanks.